Good day to you. Welcome back to Anagalactic. We're in a mathematical series in a basis in astronomy. That entire photograph is made of light. So by far, most of this photograph is stars. So this is a Hubble photograph. That is ARP 273. We need to understand the light that makes that photograph. That light in that photograph is a quantum phenomenon. And whenever you hear quantum mechanics being spoken, it could be spoken in one of two contexts. You want one definition, not 10. The words will sound progressively more philosophical the more general you wish to speak about a topic like quantum mechanics. It's the nature of a paradox that it forces out this kind of like strange mush. Because if you try to describe what it is, you simply can't. But you have to try. And so we say quantum mechanics rather than quantum paradox. So it turns out that the photon is a real thing. It's amazing to be able to say that so certainly, but there is a whole list of footnotes. And let's just start at the top with the most amazing aspect of this particle, I suppose, is that it is a particle that can either, and this is a new use of the word either because it's superpositional now. We're going to have to say more than one thing and then try to make them mean one thing. So you really have to choose which two things that really are not like each other at all. If one thing is not like the other, but there's only two things, well, how far can you take that? Well, we actually have to take it to the limit. So we're going to do that now by actually stating what the paradox is so we can frickin' answer it. Because you can't answer a question that you don't know what the question is. So we're going to take yet another try at the old gong, only this time we're going to hit it. We're going to actually get this right now. So this is how you do it. I hope you're excited because I'm giggling like a schoolgirl. I can't believe my emotional content here. Perhaps it's, let's turn that off. Maybe that's what's distracting me. If I can find the tool. Oh my god. Okay, I think this is it. Oh, goody. All right, let's just move this to center stage here. I'm going to show you some more stuff in a second, but not yet. Because this is important to get out since no one in human history has ever been able to get this out. So forgive me. I hope you can understand. Nobody's ever been able to do this successfully. So I kind of need to let you know why it's so difficult to do. And here's how I'm going to approach it with the photon. It really is the classic example. And again, I'm giggling because there's the double slit experiment. There's frickin' light polarization. There's entanglement. You know the whole list. There's just of crud. This is just unbelievable stuff. It's just defying relativity. Well, let's get at it here. What happens when you describe the quantum mechanical paradox in terms of quantum mechanics? What you get down to is what's mechanical about it. Well, what's mechanical about it is what you can measure that's mechanistic. And that basically means position. Now, very often you'll hear that momentum is added in there. I think you understand now why if you've been listening to any of the last 3 lectures. But let's just summarize it. That is the nature of science to be able to do this. So what's the big gumdrop we got out of that? Well, the big deal that's been going on for centuries that's now just really, we've reached the limit of that, is a particle. A particle. Well, what is a particle? Well, a particle has position. And it turns out that's just about it. That's what a particle is. It's a little, well, it's tiny. You have to say this is at the limit. I hope I mentioned that this is at the limit of what can even be measured. That's exactly what we're talking about, is the limit of what can be measured. Well, you might ask the question, what do we measure? Very good question. What do we measure? Position. Well, then you can also measure change of position, but you know what you have to introduce in order to talk about change of position, which is momentum. Well, we discovered what that is mathematically in spherical geometry. And I think it was worthwhile that we did so, because now we can apply it to a quantum mechanical situation that so far has had either no solution or the most number of crazy solutions of anything that's ever been hit in physics. The collapse of the wave function does not only apply to the photon, but typically, and really in its simplest form to understand, the collapse of the wave function is the way light arrives. When light arrives at an atom, what's happening is a photon is intersecting an atom. And we have to say it that way because the atom has structure. And if you want to be more specific, you can, because we actually know exactly what that photon does. To a certain threshold, we know exactly approximately what it's doing, or vice versa. But the end of the flight of the photon can be localized to when it contacts, but it does take some certain geometric insight into what you're actually seeing at that scale. And where it breaks down into a paradox can be shown in what happens when light reaches its destination. Because first of all, you have to know where it came from, and we're simply going to give the most typical example, definitely well known, the emission of a photon from a star. That's the macroscale object that has the atoms. There are atoms, and to just say other things, but atoms really of hydrogen that emit, and not just hydrogen. But it's coming from an atom in a star, and it's a packet, we say, and it turns out that's correct. It is a packet, but that's kind of ambiguous. It's like, packet? What kind of packet is it? That has been extraordinarily difficult to answer because of its behavior. And so when it leaves the electron, really the electronic shell system of the atom, this is the most typical release of a photon, and it flies through light years of space. However many of those is a damn long way a year for that photon to travel at the speed of light. So then it finally arrives at your retina. This ultimately goes into the human eye, even if it's through the medium of a photograph. Oh, those darn photographs. Let's take another look here. Good look at that photograph. Yeah, that's not bad, huh? So we get a very good portrait of distant objects from the light they emit. This would be galaxies, absolutely. Not limited to galaxies, though. Black holes are much more difficult to see. We're getting around to those massive objects, which need to be understood, and with the correct geometry, they're quite understandable. But it does lead to some pyrotechnics, because those things explode. The way to get there is first for us to understand light, because that's how we get all of our information. And it's not just what you see in that photograph. We also get a spectrogram. So that's how we get all our information. And now we need to know how that light is doing what it's doing, because it does change a little bit. It's called the redshift. But the information merely, I guess you could say its battery drains a little bit on the way. But when that photon arrives, it arrives intact, as if it had never been anything else. But during its flight, it was something else. It was not a particle when it was traveling. So that needs to be answered, and essentially that is the answer, but that needs to be explained because it sounds like, it sounds like a paradox. Well, the answer to the paradox is that that photon exists in two dimensions, and we can only see one of them. But when it's in free fall, it's no longer a particle at all. It changes from being a particle, which is the only way we can see it at all, is when it's a particle. So it has to be a particle. That's why we call it a particle. That's why we call it by the name photon. It means particle. But when it's traveling, it's a continuity. It exists in another dimension. And that dimension simply cannot be seen. But to say that it's unreal is incorrect. It's just as real as space. But it's not space. It's superimposed on space. So that is a mind bender, I should have to say. But the way to describe the collapse of the wave function can now be done geometrically. And I've proved that the mathematics is consistent, but there's a lot of work to be done, and I'd like to introduce you now to the Fermi edge of microphysics. Subatomic physics, where it reaches the Planck limit. The Planck limit can now be defined and visualized. In order to do so, we do need to penetrate on the way. The way to get at the Planck limit is to penetrate the quantum paradox, and the way to do that can only be mathematical. It has to be mathematical because we need to see it geometrically, but we also need to be able to measure it. So without the attached number system, spherical space would be worthless. But it does have an attached number system that's the direct ancestor. On our timeline, it's not the ancestor, but it turns out it is the ancestor of our number system. That we're not deriving a number system. We're finding out that we can integrate the number system we have into a two-form. Currently, we use a one-form number system. One form. That's where we get 1D from. That's also why we call 0, 0D. I hope you realize what a morass that causes. Instead, we find out that the number system we use contains the numbers that are used in the forerunner of our linear number system. And the formal name for the parent of our derived system of single component numbers has a new name which I had to invent since nobody's ever noticed this. It is the spherical number system. It should be called, in my opinion, by a different name, but that's its correct geometric name. But if it's a number system, it should be required that you don't use a geometric name, but you can combine these because it's both the geometry and the number system at the same time, which is also true for the linear number system, which is the line. But this is the sphere, and they have only one relationship. The line can be computed into the sphere by choosing a radius. And if you choose a radius, which we do, then you can fully define the sphere on a relationship between the number system in the radius. And the number system in the radius is definitely the linear number system. Now, the way we use the linear number system, that closed ray can be extended in both directions beyond the linear singularity at 0 and beyond the outer limit, which we would call numeric infinity. And that, well, actually, this would extend it to infinity. But we can also go through the center. And that produces the negative numbers, which we have found useful, to put it mildly. So the linear number system works. It's an amazing number system, and it's flexible. We have flexed it to its maximum limit with the calculus, the sine-cosine relationship, and complex numbers. And beyond those kludges, those bubblegum bandages, bandies, band-aids, beyond those little adhesive pieces of crud, we need to finally penetrate why we had to invent those tools. And the reason we had to invent those tools is we did not understand how to use numbers the way the universe uses numbers. And it is by far the superior method. What we got from the linear number system, among all the other gifts of this miraculous derivative of the universal number system, the number system for Earth until 2022, when I discovered the original number system, that really is what it is. We have gotten technology. We have gotten the ability to fly through outer space. These are miracles. By Arthur C. Clarke's definition, we have reached the miraculous phase of humanity. And I find that just to be overwhelmingly everything. It's overwhelmingly obvious, but it's a remarkable thing with things that are overwhelmingly obvious to humans. It's baffling. We have found the quantum paradox to be baffling. But when it's viewed correctly geometrically, it's actually not baffling. But let's work out the actual geometry for what happens when a photon goes from atom to atom on the straight line. This is our original perception of straightness. The photon exhibits linear direction. That must be explained because it's impossible. That is the quantum paradox turned around. There's no way that that photon can go on a straight line to a photographic plate because it's propagating spherically. The reason we're forced to say that is that it's propagating invisibly. When the photon is between atoms, it is completely invisible. It disappears from space. This can be proved that that's what happens during the transit of this particle. That when it leaves the atom, and you have to be specific when it leaves the atom, this would be in a discretum of time, a tempescule, a unit of Planck time, that it detaches and disappears. It disappears. And then when it gets to the photographic plate, with a spherical radius of light years, that is the wave that collapses. It collapses back to a particle. And therefore, the idea that that was a particle has to be defined more carefully. Whatever you say about that particle, you have to include what it was when it was in flight, and that is the quantum jump. When it left the electronic shell, that photon could not have done so in a quantum leap. And yet that's how we measure it. Why do we measure it that way? Because we can't help it. Because otherwise it would be immeasurable. If it has no position, what is it? It's a continuous thing. It's not a particle. It is the continuum. It transitions from spatial space to another space. And while it's in that space, it moves in a straight line to your photographic plate. And it never did anything else. It's just that it did it in all directions at once. That particle went in all directions at once. That means, and this can be proved, and we essentially have already proved it, but let's state it. It goes into the perpendicular realm. And that's the ultimate spooky. It perfectly describes why we can't see it. We already know why we can't see it if it's perpendicular. Because when you see, you're seeing on a radial line. You're seeing spherically on a radial line. But what you can't see is the propagating sphere of light. And that's a sphere. It's not a line. We see on a line. We do not see on the perpendicular line. That is the spherical propagation called a wave. That wave is a sphere that's perpendicular to the radial line of your center. And that thing, in order for it to arrive and be interpreted, indicates that you are some kind of center. You are. And that's the spooky part that includes the human. That is the observer. That is the one who takes the measurement. It goes into your brain. And that's the completion of the flight of that photon. That's how it gets to you. It goes through a perpendicular dimension to space. And in that dimension, it is still a particle with an expanding radius of imaginary spatial space. So that is expanding through real space that we cannot see. And we cannot see it. We can only describe it after we saw the effect of the change of dimension of the photon. The photon changes dimension out of space. Now, in order to solve the paradox that results from saying that, you have to state how come then it's going through space. And the right answer, essentially, is that time is going through space. And so it has to do with motion. And so the relationship between space and time has to do with motion. We call this, from one perspective, we call it light speed. That is something that needs to be described now more carefully, since we can see it geometrically. It's an expanding sphere in contraspace. That means that it's in free fall. It's experiencing anti-gravity because it's being attracted to the centrifugal pole. It's going away from a protonic center. To the proportion that the proton forms a center to space, whatever you might say that is not the proton, or maybe is inside the proton, gamma rays can be emitted from a mechanism inside the proton. The smallest frequency wave known to man, measurable that is a gamma ray frequency wave that's emitted from a proton. In other words, it comes from inside the proton, not from an electron. But of course it has a very tiny wavelength. So protons do not emit light. They emit electromagnetic radiation at an extremely high frequency. That's the right way to say that, and that answers a question that one of my viewers asked. And I thank you for asking that. It took me all this time to answer it. But that's essentially electromagnetic radiation, and that's the more generic name for what includes light. But light has a lot more frequencies than the gamma range. And for light to be emitted, that comes from electrons. And it only comes from electrons. That's the only known source of light, is from electrons. So they produce photons, and so the photon has a direct relationship with the electron. And so what Max Planck was forced to call a quantum was actually a wave. And that needs to be explored a little more carefully, but what we're doing now is summing up the primary relationship between the wave and the particle, and now we know what they are, because the photon defines what they are. The photon is a particle in free fall. The proton is the opposite of that in every way. So we can disregard the proton except to say that it is a space particle. The photon is not. The photon is an event particle. It's an event particle. And it has a certain frequency and a certain wavelength that we just discovered are exactly on the proportion of a divided continuous line. That is called a sphere. A sphere cannot be divided unless you put the equivalent of points onto it to divide up its rotation. When you do that, they are not spatial points. To picture them, to visualize them, you have to assume that you're seeing them as points that you're putting on the equator of rotation, which is the eigen of the sphere. So the eigen of the sphere is that circle that we can see and we can put points onto it. When we do, the lowest number is 2. That is the lowest frequency in the range of frequencies, because anything less than 2 is 1, and that's no motion at all. We just proved it, because when the sphere has a value of 1, it's not rotating. But when it has a value of 2, it has the primary oscillator imposed on its rotating surface, and that produces the click, 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 click. That click happens twice on frequency 2. Click, click. It's actually click, click. It'd be twice as fast. As no rotation at all. But there's no such thing as no rotation. That's another way of saying that we cannot actually see this sphere. And the reason we can't see the sphere is we can't see the circle. And the reason we can't see the circle is because we can't see the sphere. You could say it that way, but there has to be a reason We see neither the sphere nor the circle. And the reason is that is a particle that's traveling on a straight line through time. That's its frequency of time, is 1. It stopped moving in space and is now traveling in time. A photon only travels in time, and time goes out. It does not go in. It's the manifestation of centrifugal force which we can pick up with our brains and minds. Using our physical sensors, our physiological sensors, we detect centrifugal force, not gravity. The opposite of gravity. It's anti-gravity. Only the photon can achieve anti-gravity. But isn't that an interesting way to say it? There are only 2 ways to fall in this universe, because the entire thing is the integral of gravity. That can be proved. It has been proved. It's the integral of gravity. Well, doesn't that mean it has a center? Absolutely does. How big is that center? It has the radius of time. So if you can find out where time transitions to space, you can plot the curve. If it's a force, it is a force. There are 2 forces in the universe that are balanced on the Noether-Boschkovich balance. And it perfectly describes the atomic system, but it also has ramifications in our interpretation of gravitational force. Even though it's an integral, we do not fully understand gravity at macroscale. And I'm going to give you a specific example of how I know that, because I have the right answer. This is what science wants. When you use spherical space as the correct geometric approximation framework for analyzing either light or gravity, you find out that when you switch, that you're no longer using a grid. You no longer accept linear space. You're now measuring with the integral system. You discover things. Relationships that you did not surmise could be so simple. And one of them is the correct definition of the collapse of the wave function, the foundation of quantum phenomena. We will also fully explain right now the nature of entanglement, and every Bob and Alice experiment will be answered right now. All these conundra, if that's the plural of conundrum, all of these paradoxes come from one fundamental geometric fact, is that we've been unable to realize that the dimension that we cannot see is not time per se. It's the domain that in a specific sense is parallel with space. Now, Einstein didn't say parallel. You could also say polar space, in which case it's strictly in and out from a center. But we can't find that center to the same proportion we can't find that edge. Astronomy cannot find the edge. And quantum mechanics cannot find the center. That means they're related. Both of them have limits, and that's our physiological limitation. We simply cannot see the center because of some geometric reason that must be explained. Well, the reason we can't find the geometric center is that it's infinitely small. What's interesting is when you switch to the spherical number system, you find out that infinitely small does not mean 0. With our visual onboard system, the way we perceive space and depth and inner and outer, when we go in, we assume that the center has to be 0. We were told that. There's a reason why we have to have A0 for some useful purpose. It's in order to have a beginning of a linear trajectory. You can't have a linear trajectory without a 0 point. A 0 point. But if you interpret that to mean that that's the geometry of the universe, you made the fundamental error of geometry. You have to consider the embedding space, which definitely is not linear. Therefore, you have to prove, as I was forced to prove and did prove, that linear space is the derivative of the higher space, you could say. It is higher, it's bigger in every way. The sphere, when you draw a line from a center, you're making a sphere. You can prove that the fact that you can draw a line means that you can visualize a spherical embedding space. Is there an embedding space for spherical space? Yes, there is. And it's science fiction-like. The reason it's science fiction-like is because it's science, not fiction. But it sounds like fiction. We should be used to that by now. So what is this new science fiction? It is that the Einstein 3-1 split is on 2-2 space. His 4 dimensions were split wrong. If you have 4 things, how many ways can you split them? You could start out with you don't split them at all, or you take unity. Okay, well, let's put that in a footnote. You could split it right down the middle and have a 2-2 split. Correct? Yes. Is that what Einstein did? No, that's not what Einstein did. What did Einstein do? He used the 4, he started with the 4, and he split the pinky off. You hold up these 4 fingers, and instead of making the Vulcan sign of whatever it is that's nice, you hope, it's interpreted that way. But if you split off the pinky, which is, by the way, hard to do, because the tendons for these last 2 fingers are kind of related. And so it's hard to, well, look, I don't know how I did that, but I did. But that's time. Well, you can see that that doesn't work. Because here are 3 lines for space. And here's a line for time. And to add insult to injury, Einstein had to make it negative. That's literally true. So this is a pure mathematical construction using linear mathematics. Well, could we do better? Theoretically, we could, if we could prove that space is not 3-dimensional. I hope you realize that it's not. Okay? It's a very useful, technically it's a projection. It's a projection of a cubic lattice over whatever space actually is. Well, we have a pretty darn good idea what space actually is to a much better approximation called the integral. Instead of seeing it cubically, which is derivative, see it the way it really is by integrating the grid. Well, when you do that, you get a bunch of packed spheres if you're thinking linearly. But that's not the correct way to look at it. Instead of assuming everything you assumed with the line, You simply begin by observing that it doesn't begin with a line. It begins with a sphere. That can be proved mathematically, and I've done so. And so is Max Planck, and really so did Einstein, but it took a synthesizer, a synthesist, a logician, a geometer. I've used the word geometer, and more than one person has not known that that's an actual word. And that was my first reaction. That's not a real word. Because I never heard anybody when I was growing up say geometer. That probably indicates my cultural background more than anything else. But a geometer prefers to see reality the way it is, which is not necessarily numeric. Well, if you're using the wrong number systems, the linear number system to compute spherical space, well, obviously it's not going to work when you reach the limits. Well, does spherical geometry work when you reach the limits? Yes, it does. And the reason it does is it utilizes the original line. There's no such thing in the universe as a line. I hope you know that. It's a purely geometric impossibility. But what you can do is make line segments. Now, in our interpretation of the linearity in spherical space, there are two lines. And it really incorporates everything we know about the straight line, because the real straight line, the way the universe works, is you take the one and only straight line, and that would come from the one and only center. So you start the numeric system with the center, and it turns out that it has the numeric value of 1, and that's the center of universal space. What is inside it? We can see geometrically there has to be something inside it if it has a surface value of 1, which, by the way, indicates exactly what its radius is with an irrational number. It's the reciprocal of tau. So the radius of this circle, if you say that the surface, I alternate between circle and sphere, and I'll show you why in a moment. Well, I want to stick with sphere, though. When the surface value of the sphere is 1, essentially that means that there is, it's ambiguous what's inside of it if the sphere's surface is 1 itself. Well, that 1 itself has a peculiar shape, doesn't it? Yes, the 1 has a shape. But not when it's written as a 1, because that's a 1 component number. We see the 1 as being a linear 1, which means that it's just one thing. But the universe does not treat the linear 1 as one thing. Instead, the universe starts out with a split 1. And it does this in order to avoid nullity. And this answers the ancient paradox of why is there not, never, nothing, like not forever, forever, there was never anything ever to begin because there never was nothing. That's quite a paradox, and even difficult to say. I hope I did that well. But a paradox forces you into a circular, it's called a loop. Or a circular argument is a variation of this loop. Is you got the edge? What's beyond the edge? Well, another edge, something beyond the edge. That's infinity. Going in, you encounter the impossibility of division. The impossibility of further division. And that's a universal speed limit that's equivalent to light speed. But in geometry, you can't divide the final number. And so there is a lowest number in the universe. In any way that we construct the universe, there has to be a lowest number. And that's expressed again on the split 1. That lowest number begins on a sequence approaching the lowest number, correct? Well, what's the highest of the low numbers? That's 1 over 2 or 1 proportion 2. What's the lowest of the high numbers? That would be 2. And so 2 takes on a special significance in spherical space. And we're coming up on an hour. We haven't gotten around to the supermassive black hole yet. I promised that. But I wanted you to have a better interpretation of time. That it occurs in event space, which we can't even see event space, but that's the space in which the photon rides. And that continuity in which, that's the circle, by the way, or in this case, the sphere. In real space, it's the sphere. And that photon occupies that sphere at all locations at once. And it's still a particle, but it's everywhere. And then it just falls out as a particle trying to reach the edge, and that is hyperbolic space. So it's falling hyperbolically, but on a median line called a parabola, or a paraboloid. And it's falling at the speed of the paraboloid opening, because it's in perfect unison with the speed of contraction of space. When you integrate gravitational space, which is to integrate all the protonic centripetal force, when you integrate the protonic centripetal force, you get the gravitational force that holds up the universe in one pillar. But according to even Newton, but formalized by Emmy Noether, who got a Nobel Prize for her discovery of force symmetry, that is force balance, which was also discovered by Ruđer Josip Bošković, and both of whose work I've consolidated with that of Einstein and Planck. And finally, we are now able to tackle the Dirac equation, and we will rewrite it now. But first I'll give you the secret meaning of the supermassive black hole, which I have renamed because that's a ridiculous name. And for such a grand, magnificent object, I introduce you to the realm of the big cats. The realm of the big cats. And you'll soon come to love the big cats. They're SMBHs, they're quasars, they're AGNs, they're DRAGNs, and they are magnificent. Especially for us guys, it's the biggest explosion of all, and it's happening all around us, and we are in for a treat. Stay tuned, and don't forget to keep looking up. Right now it's cloudy here, but when it's not cloudy at night, take a look. You'll never regret that. We'll be right back.